Hi, welcome to the Natural Language Processing lecture series. This is lecture number one. We'll be learning natural language processing from scratch, basically by relying upon two different material of syllabus. One is the practical natural language processing book, and the other one would be our NVIDIA certified associate examination syllabus. Fine. So we'll start off with why are we even processing language? Why is it even important? Why are we even learning this, right? These questions usually occur when we start learning something from scratch. So as well, I'll be dwelling upon these and then we'll proceed further slowly with more advanced topics. Fine. So languages and our species. Observe this image carefully. We started out this way. Our ancestors started out this way they were hunters and gatherers. They collected all of their wisdom, information, knowledge, used the carvings or the rocks as a medium of knowledge transfer through language, and then transferred or shared their knowledge through language to their next generation and the other individuals. This accumulated slowly but steadily to an extent that they were able to develop the whole society with their accumulated knowledge. Generations after generations, the future generations of their offsprings, they were able to get all of this collected wisdom and information and build on top of each other to transform their whole society. So we were here, we slowly transitioned to this phase, and then we transitioned to a more trade-oriented, global trade-oriented phase with barter system, and then currency was invented, and all of that happened. And then from 20th century, we have been into this phase of digital era. Fine. This basically happened through two different revolutions. First, the industrial revolution, and then the second is the digital revolution. I'll be going to the digital revolution directly because industrial revolution basically made our survivability as a species more organized. And then the digital revolution has led to the democratization of information or knowledge in general. And that is why we are seeing innovations each and every day. So with this digital revolution, the information accessibility has increased significantly that each and every individual on the planet in any nook and corner geographically can access, learn, discover, innovate, and also document their new innovations or their new knowledge that they've gathered or they have found. So this information accessibility tool through the tools such as the computers, starting from basic desktop computers and the PCs, personal computers, and then the smartphones. All of these have significantly increased the frequency of knowledge sharing and the accumulation of knowledge and the whole process of working on top of each other's knowledge base. All of this has significantly improved our overall advancement as a species. So we need to be thankful for this digital revolution. But then, what is the main core part of this digital revolution? If you see, human computer interaction has played the most significant important part overall. Because starting with computers, our information accessibility has become more easier. The more easier and quicker the information accessibility and documenting of new information and knowledge transfer, all of this happens. The accumulation of knowledge happens very fast. With accumulation of knowledge, society overall builds with that knowledge and wisdom and advances faster. This is exactly what this image shows. Interesting, isn't it? So we started here and then we went all across, and at present we are here in the digital era. Now, I want you to recall what made this whole in digital revolution along with this information accessibility even possible, are told regarding something called as human-computer interaction. Human-computer interaction has made the significant contribution for all of this evolution to happen. So what is this jargon? What is this human-computer interaction? We'll go and see what is this specifically. So the event of communication between a human and a computer could be known as a human-computer interaction. And this particular interaction between the human and the computer happens through an interface. Interface is the medium through which this communication happens between the humans and the computers. So these interfaces could be a form of technology or a methodology or any tool. So it is just a tool or a methodology or a technique or a medium through which we communicate to computers. Right? Fine. So what are the major 3 characteristics of this tool? What has it done by paving way to the human-computer interaction? By paving way to the human-computer interaction, it has increased the usability of information. Before even increasing the usability of information, it has first increased the information accessibility. So it has democratized information access. Second of all, it has developed a medium for the whole species for quicker knowledge transfer. So it has become a medium of knowledge transfer for quicker knowledge transfer or communication or communication between 2 different humans or individuals across the world regarding any new innovation or anything. And then by indirectly contributing to quick knowledge transfer, it is increasing the usability of the information. So whatever knowledge is accumulated or transferred via this medium or this tool can be used by any human on the planet, and it can even develop on top of it. So increasing the accumulation of knowledge. So indirectly, by contributing to human-computer interaction, this tool, human-computer interface, has paved way to the whole transformation of our society. Now we'll see the interesting area of how this particular tool, human-computer interface tool, has evolved all along. You see the evolution of HCI, or human-computer interface. We started out with early mechanical axles in the first industrial revolution. If you see the First World War, the whole computer was fitting a whole room, right? There it was all mechanical axles. Even the first Turing machine, which Alan Turing invented, was actually a mechanical operation-oriented computer. Then we went on with punch cards, and then slowly went on with physical computers, and then touch screen. And now we are in this phase where a natural language text can be given as an input. We are transitioning to that phase where we can directly interact with computers using a natural language. So this has been the evolution of HCI. So that is why it is very much important for us to know how this natural language is being processed, because with natural language processing, imagine if we have a tool that is able to understand what we say directly, then the information transfer or the knowledge sharing will become even more easier, with more easier and quicker information transaction. We'll be able to accumulate knowledge faster, build new things on top of each other's knowledge, and then advance our civilization as a whole. So, but then we might have this question: how do we make computers even understand the natural language? So for that, we need to know one specifically before even going there. Computers understand only numbers, right? So and that too only binary systems. So how do we make computers understand natural language? For that, we need to first understand what is even a language itself, right? First, we need to understand what is the language, and then only then we'll be able to numerize the language and then process it. Because only numericals will be processed by computers. That is, they are called computers because they are good calculators, right? So we need to find a way to numerize the natural language. But then to even numerize the natural language, we need to understand what is the language. How can we represent languages numerically so that it is processed much efficiently and it simulates human understanding. The tool simulates human understanding, or make a tool that simulates human understanding. Fine. So that is why we need to understand what makes up a language. So we'll see what is language. So language is a structured system of communication acting as a tool to convey meaning with several constituting components. There are four. If we further break down the language, we have four different parts. At the upper layer is the context. If you go even further, it is the syntax. Even further, it is the words. But then, if you take overall, it's the sound. Sound makes the word. Words make the phrases. Phrases make the sentence. Sentence give us a meaning. Any phrase that gives meaning is called a sentence, right? We'll understand what is context first. For example, if there is a particular word called bank, this word could mean different in with respect to the sentence where it is being positioned or placed, right? It could mean a river or a side of a river, or it could mean even in financial institution, right? So context means this: the meaning of the word or interpretable meaning of a word will change with respect to its position in a sentence or its use in a oral passage or a sentence. Fine. So what is syntax? Syntax involves phrases and sentences. Fine, we'll see what is syntax and grammar. So syntax is basically the grammar. So we'll be going back to first standard, I guess. We learned about noun, determiners, noun phrases, verb, determiners, prepositions, all of this. So I'll give you, we'll see just two sentences as examples. The first sentence is, the boat sailed up the river. Second sentence is, the girl laughed at the monkey. Both of these are different sentences. They aren't similar to us in terms of meaning, but then they're syntactically very much similar. To give you an understanding, see this. So we have a determiner and a noun. Put together, we'll get the noun phrase. Same thing applies even here at the end of the sentence. The monkey, the river, similar syntactical structure. We'll get the noun phrase. And then when noun phrase combines with the preposition, we get the preposition phrase. And then the preposition phrase, when it combines with the verb, we get the verb phrase. So all of this put together is a verb phrase. And this one is the subject to the noun phrase. If we add both of these, or if we combine both of these, we get a sentence, a meaningful sentence. So this is how we actually see language syntactically and then say two sentences are similar to one another. So this could be a way to make computers understand language, isn't it? It could maybe help them compare two different sentences using syntax, or we can numerize the words and then make them compare. And then, so that's why we're learning this. What is a language? The components of a language. Fine. So syntax and grammar rules are fine. I've given examples. So what about morphemes and then lexemes? We'll see. And phonemes as well. Phonemes, we would know obviously from the school. We learned about phonetics, meaning the sound or pronunciation of a word. Fine. So phonemes are just the sound of the word. Bat, cat, the ba, ka, da, dog, da, fan, fa, yes, or yes is yeah, and then the shop is sha, chip is cha. So all of these sounds actually form the phonemes, so the phonemes part of this language. And then lexemes and morphemes. Interesting distinction, right? Lexemes encompass all forms of a language or of a word. For example, I've given an example here. So if there is a word called cat, all of the different forms of this word or different derivatives of this word would be cats, a cat-like, a cat apostrophe s. So all of these can be represented using single lexeme called cat. This is actually what is called as lexeme. or a lexicon. Fine. But then we'll see what does the same word mean in terms of a morpheme. Morpheme means it's the smallest unit of meaning, right? Here, a cat will mean the actual meaning of what this word represents. That would be known as a morpheme. So this is the major difference. So why are we even learning this? There should be some applications, right? So we'll see what are those. Applications of components of language. From the phonetics, phonemes, we'll be able to use them for converting speech to text or speaker identification or text to speech. For morphemes and lexemes, we'll be able to tokenize them. I'll be going through in detail about each and every technique mentioned here. This is just for reference. We'll see each and every technique mentioned here in specific details, right? This is just for your overview, right? So these different techniques can be done using each and every component of the language. Fine. So we know the components of the language. We can directly process them. So why not? So that is all. That is all right. Done. We're done with NLP. Isn't that? Is that the case? No. No. So I'll give you an example again. It's not that simple. Take this sentence as an example. The dog chased the cat and it ran up a tree. What do you mean when you say it here? Is it the cat or the dog? Ambiguous, right? It is ambiguous. So this kind of sentences is where it is very much difficult for computers to understand, even for humans to understand, right? So these are the challenges for processing language. So it starts with ambiguity. Ambiguity meaning a particular sentence can mean a lot of things. For example, like how I said this could be either a cat or a dog, or even this sentence, I made him duck. It could be between say WWE fight between two fighters. Made him duck when giving a punch or something. So and then or it could be someone playing a cricket. Oh, I made him duck in the first ball or something. So the ambiguity lies with the sentence, with where it is being used. So that is one thing. Second one is the common knowledge. A computer cannot understand. Syntactically, this is actually almost similar, right? And then even the words are all similar. If you want to represent the words using some particular number, the collection of numbers is also similar. So as per the computer, these both are actually same. But then there's a common knowledge that this is not the same. Man bit dog, dog bit man. These both are not the same. So how will you make the system understand this? This is a major challenge. And then we have creativity. So we have seen linguists have different poems of different styles. So how will you make the system understand these different styles of poem? Again, a difficult task with numbers. You have to numerize all of them and then make computers understand it. It is a difficult task again from a statistical point of view. And then you have the diversity across language. Each language will have its own different grammatical structure, its phonetics, and its own flavor of how they see or perceive a particular object and all of that. So again, that becomes a challenge in processing languages. So these four challenges have created or made researchers to spend years of their time working on natural language processing, and they're still overcoming the challenge. We have overcome a lot with the recent DeepSeek large language models and all, but then we still have a lot to go further. We still have a lot more technological advancement to be done for it to be perfect. All right. So overcoming challenges with various techniques. We'll see an overview of this. So we can see specifically for NLP. Only a smaller part of the NLP segment is inside ML and DL. Most of the part is actually on the AI side, right? So there are a lot of techniques that we use in NLP that we are not taught in ML or DL. There is not where we don't use ML or DL techniques. After decades of research, we have come up with three main approaches to solve all of these challenges for NLP tasks. Those three approaches are the following. So the first one is the CFG heuristics and rules.
CFG stands for context-free grammar. So in the first approach, we'll be having two parts. One is the CFG, that is the first part. Second one would be the heuristics and rules. For giving you an example of what these heuristics and rules would be, uh, I'll just say this. So there are three main conditional statements, right? If, then, and else. We would make up rules using these three conditional statements, and those would be used for specific NLP tasks. So this could be a direct rules-based system, right? So this would be our first approach. So the first approach has two parts. One is the CFG, and the other one would be the heuristics and rules. CFG is the mother of all of NLP tasks and NLP systems that are currently present, right? It is the basic root of any NLP system. And the second approach is where we have this machine learning approach. So machine learning approach does not start as it is directly as machine learning. Instead, it started out as a statistical model and then evolved to become a machine learning model. Fine. So in machine learning, we'll be specifically seeing four main approaches. First one is the name-based classifier. Second one would be an SVM, support vector machines. Third one would be our hidden Markov model, HMM. And then the fourth one would be our conditional random fields. So these would be the four popular machine learning models that are used for solving NLP tasks, right? So out of all these four models, hidden Markov model alone will be seen in detail because we'll not be using hidden Markov model or we'll not be even going into hidden Markov model or even using it in our further lectures. So we'll just see the details of hidden Markov model in this lecture itself. And the remaining three models will be gone through in brief to give a glimpse of how these models are, how do they work, and all of that, right? So this is the second approach. And the third approach is the deep learning method. So in deep learning method, we have several algorithms. We'll start off with RNNs and then the LSTMs. RNN stands for recurrent neural network. LSTMs are long short-term memory a type of RNN. And then we have the convolutional neural network, CNN. And then we have the transformers. And the transformers based BERT we'll be seeing, and even the autoencoders. Fine. So these are the algorithms that we'll be seeing in deep learning, and this will be the third approach in our overall three approaches for solving NLP tasks, right? And before going in detail with the first approach, let me just tell you this specifically. If you're getting into NLP now, make sure that you finish all of the fundamentals of machine learning. Finish understanding the fundamentals of machine learning and only then get into NLP. So the first method is context-free grammar. But before getting into this context-free grammar, we'll have this scenario of you first think about this. We are learning about natural language processing. Fine. Okay. So natural language means all of the English words or any of the mother tongue, all of these would be natural language. Fine. We saw even the components of language. Fine. But then how are even computers able to understand programming languages? Even the programming languages have keywords and all of those things which are similar to English, right? So how are the programming languages able to understand that? So a system that could understand the programming languages could be the first type of NLP system, right? So the compilers form the first type of NLP systems. So if you see in that context, you will understand how profound this particular technique is. Context-free grammar was invented in the year 1956 by Dr. Noam Chomsky. He's currently working as a professor at MIT. Fine. So the technique that he invented, the context-free grammar, is this basic fundamental NLP technique that all of the programming languages used. It was the same technique that was used even for C programming languages compiler understanding thing. So for the compiler to understand and validate the syntax that is written in a programming language that is similar to a natural language, that actually happens through this context-free grammar rules. Fine. So he came up with a method or a set of rules that could form a grammar for all of the programming languages, and that was the context-free grammar. Fine. So that profound is this particular technique is. So this is the first type of NLP system ever to be created. Only after that, we were able to even compile the programming languages. And only after that, we were able to develop program softwares. And then we have evolved this much that now, even if you give natural language text-based input to any of your chat GPT or your DeepSeek, it's able to learn from it, or it's able to answer based on your question. It's able to understand the question and then answer for it. So that is how we have evolved. So this was all invented by this guy, this legend called as Dr. Noam Chomsky in the year 1956. And he's even alive now. He's working as a professor in MIT, right? So he's a renowned linguist. The main important another thing to recognize or to observe here is he was a renowned linguist as well. He's a linguist as well as a computer scientist. So he was able to understand the language and make sure he was able to make sure the computers understand our language. That's how he came up with this method. So that was a requirement back then. If you have to become a computer scientist or a person who develops algorithms for making computers understand language, you will have to be even a linguist to know what a language is first of all. And only then you can get into become a computer scientist, and then you can combine the two domains to come up with your own system or a technique like this, right? One more thing what you have to know is the context-free grammar was introduced in the year 1956, but then the C language was then only in the year 1972. So they had a lot of time to improve this context-free grammar to an extent, right? So C language was invented in the Bell's Laboratory in 1972. So what happened is they added some more different context-sensitive rules to make the C language more comprehensive. That is why we have all of this meaning understandable variable declarations and all other context sensitive rules that are there in this C programming language, right? So this is the whole thing. So we'll see the applications of context free grammar. Like I said before, context free grammars are used in the compilers to parse the source code and indirectly help computers understand programming languages like C, Java, and Python. And of course, since the programming languages are almost similar to natural language, we could say that it is used for natural language processing, specifically for modeling the syntax, right? So this was the main application of context-free grammar. Now we'll proceed on to what is this parsing. Before that, so we saw this application of one of the applications of context-free grammar as parsing source code, right? But then we don't know what is this so parsing. So that is where we'll understand it's a jargon. So we'll understand what is parsing. Fine. So there are two types of parsing. One is the source code parsing, that is the ancient technique, and next one is the document parsing. Document parsing is what we'll be seeing in the future lectures, where we'll be seeing the whole NLP pipeline, or how we process the text, how we get the text, all the language text, words, and all of that, and then how do we process it. So for obtaining the text, we use this kind of document parsing. So the goal of this particular document parsing will be to extract content, text, image, all of these data from the documents such as Word documents, PDFs, or any external documents. So that is exactly where this document parsing comes into play, right? So this is the modern technique. Fine. The ancient technique is the source code parsing. Source code parsing is where the compilers come into play. So compilers have this particular program called as parser program. This parser program goes through each and every string in the script, in the source code script, understands each and every string in the script, and checks whether these strings are in the correct syntax format for that particular language. For example, in the C language, there'll be some syntax, right? So some rules and regulations for the language is called a syntax. So this parser program will take in each and every string of the source code and then validate it with its rules and regulations, what it has as context-free grammar. So here is where the context-free grammar comes into play. It becomes a set of rules which the parser program uses to validate the strings that are there in the source code. So indirectly, it is validating even the source code or the coding itself. And then this source code is made into a parse tree. So a parse tree means an iterative movement of the cursor from one string to another string, but then while moving, it is also giving out the context or the tagging for each and every string. It's making the compiler understand, okay, this string stands for this operation. This string is that. This string is an expression. This string is a number. This string is a variable. So that kind of tagging is given for each and every string using the context-free grammar rules. So, and this parser program, using the context-free grammar rules, it's creating the parse tree. This parse tree has all of the information for the compiler to understand what each and every string stands for. And after understanding what each and every string stands for, again, the compiler takes in this whole parse tree inside and then comes up with the syntax tree. Syntax tree is where the compiler has different tasks or the operations that are actually going to happen in the compiler, or actual operations of what this program is going to do will be made into another syntax tree. And that syntax tree will be directly applied to the low level machine code, like embedded C or something. Fine. So this is the whole process. So what happens? There's a source code. The parser program runs through the source code, takes in each and every string, tags each and every string to a particular tagging expression that is there in the context-free grammar rule. So validates the whole source code syntax and gives out a parse tree. That parse tree contains all of the information about each and every string's nature or its tagging. Like this string belongs to this particular tag. This is an expression. This string is actually a number. This string is actually a factor. So that kind of relationship-based parse tree it gives out, the parser. And then this parse tree is given into the compiler. The compiler comes up with again a syntax tree. This syntax tree has all of the different operations that are needed to be performed in the low level machine code. And using this syntax tree, we are able to perform the low level tasks of adding a number. Say if that is a task, that will do that. If it is something else, so to do that. So it will all be done in this low level machine code that is in embedded C. Fine. So this is the whole process. So we have the parse tree. Parse tree is given into the compiler again to make the syntax tree. And how do we get the parse tree? We use a parser program. Parser program uses a context-free grammar for validating the source code. So the source code is taken in by the parser program using the context-free grammar rules, gives out the parse tree. This parse tree is again, it gets into a compiler and the compiler gives out the syntax tree, and the syntax tree is actually used for performing the overall operations in the low level machine code. This is the whole procedure through which parsing happens and the whole understanding of programming language happens in the compiler. And this is the first type of NLP, or natural language processing system. Fine. So we'll see an example now. So here is our code now. This is the source code. Imagine this is our source code here. This is our source code here. Fine. So this source code is given in the script. Fine. So now what happens? This source code is parsed by the parser program of the compiler. So parser program uses these rules to validate this particular string. And it even tags each and every string. So see, you can actually see. So it is tagging this digit 3 as it's a digit. It's a factor. So it's tagging even this string 4 as a digit. And then it's a factor again. And it's parsing overall all of these strings and then coming up with the taggable expression. That is an expression, term, or factor. Right. And then expression, term, or factor. So it comes out with this parse tree, and this parse tree has all of the information needed for the compiler to understand what this string specifically represents, and this string specifically represents. So the strings it's tagged to the expression. So it means, okay, plus this string corresponds to the expression. It's a type of expression. Understood. Compiler understands. Okay. And then comes down here, we have the star symbol. The star is again a string. Again, it is tagged to this T, which means it's a term. So, okay, fine. This is some kind of term. So each and every string is given a tag, and that tag is all connected via a parse tree. So this is again given into the compiler, and that is how it comes up with the syntax tree now. So directly it comes up with the syntax tree, and this syntax tree has the direct operations that are needed to be performed. See, it's directly here. So these operations are directly used for doing the actual work in the low level machine code. So this is how the whole parsing of the program happens. So hope you understood the main difference between what is a parse tree and what is a syntax tree, and what is parsing, and how the basic NLP system that uses context-free grammar understands programming languages, right? So this is the whole technique. So hope you understood, and hope you got the difference. Now we've understood the difference between a parse tree and a syntax tree. We'll proceed further to see an example of how this parse tree works in real life for a single statement of C program, right? This would be a real life example. Now, for looking as a whole, it might look a little complex, but then I'll break it down for you so that it feels like it's nothing, it's simple. Fine. I'll show it now. Fine. So this is the particular statement that we're looking through. This is the only single statement that we have from the C program's script. Fine. So if x is greater than 9, x is equal to 0, y is equal to y plus 1. This is the statement. Now this statement is parsed through by the parser program string by string, like a character by character, iteratively, right? And while going through each of these characters gives out a tag for each and every character, like how you're seeing here, right? So all of these tags and the rules for these tags are made by this context-free grammar rules. So these rules are the main rules and regulations that this parser program uses to identify this string and then validate whether the string that is observed or which is there in the source code is in the correct syntactical format or not for this program, right? There's a whole process. This is just an example of how this works. And this is a context-free grammar of real-life C program for this particular statement alone. Fine. So yes, so there are some non-terminal state symbols and terminal symbols. Terminal symbols are those symbols with which the whole statement ends. So this could be a terminal symbol. It's starting and ending. So terminal symbol. And then we have non-terminal symbol where the string or the parser expects another string to continue this. For example, a string like this is actually a non-terminal symbol. Like this one, the greater than, equal to, plus. All of these symbols are non-terminal symbols because it expects another character after it. That's why it's non-terminal, right? So this is the whole example of a real-life C program's single statement, right? And so imagine the profound impact of this person. He's still living today. Is Dr. Noam Chomsky, whom I showed before. This picture was taken in 2017. And he's still living today. He's working as a professor at MIT, right? Because of him, we have the whole C programming language. And because of C programming language and all other languages, we are able to have all of these applications that you're using from the start of your day till the end of your day, right? So this guy literally changed the world with his own invention of context-free grammar, the first type of NLP system to ever exist, right? And made even the programming language processing is possible. Fine. With that done, now I think you would have got an overview of how this CFG is, how it looks like, what it works on for, how does it work, and all of that. Right. Now we'll just see an overview of the whole characteristics of CFG. Right. So there are three main characteristics of CFG or context-free grammar. First is generative power. That is what you can actually use the rules of the CFG or the rules and regulations of the context-free grammar. Use those rules to generate your own string that becomes meaningful to the user as well as the program, right? So this is the generative power of the CFGs. And you can generate all regular languages. Regular languages in the sense, all of the natural languages are regular languages, and non-regular ones are the programming languages. So C program is a non-regular language. So that is one thing. And next we have the parse trees. So every string that is being taken in by the parser would be given out by the parser as a parse tree. So it actually tags out each and every string's attribute, and then it also validates whether this particular CFG rule is being applied or not. So this is the production rule. Production rule is the CFG rules and regulation. That is the production rule, right? And then we have the third characteristic is the ambiguity. Here, what do you mean by ambiguity here? So for a particular single string, there could be a lot variety of parse trees possible. For example, let me show you this example that we had here, right? For this particular 3 into 4 plus 5, 3 star 4 plus 5 single statement. So here is one example of a possible parse tree. Another example could be 3 on the above side, and then you could have 4 here, and you could have 5 at the last, at the deeper leaf node. So this could be becoming another different parse tree for the same string. So you could clearly see for a single statement, there could be multiple parse trees, right? So this is the ambiguity of parsing. So this is an disadvantage of CFG. That is why we have to come up with our own syntax rules to make it even more comprehensive for programming languages. So that is why C's CFG ambiguity, this ambiguity was resolved by coming up with particular syntax rules so that the parser or the compiler doesn't get confused between one type of parse tree or the other type of parse tree for the same string. So that is the whole thing. So these are the main 3 characteristics of CFG. All right. So this is how we resolved it. But then even after resolving, we were able to only do justice for programming languages, not for the natural language, because CFG is still not great. But then, before going to that, let me just give you a glimpse of what you can do if you want to really build your own programming language. So if you're really interested in this topic, and if you want to build your own programming language and your own compiler, look out for the chapters in computer science known as finite state machines, and then theory of computation and compiler design, or even automata. So all of these chapters in computer science are very much important for you to develop your own programming language. They become the fundamental concepts for building your own programming language or your own compiler, right? So next we see, this is just a glimpse of what a programming language is. So all programming languages are context-free languages. So they don't have a specific context. They just follow some rules or syntax that is formed using CFGs. But then along with the CFGs, they have this context-sensitive rules like variable declaration, type checks, and all of these context-sensitive rules. So that is why I told you, like in 1956, context-free grammar was invented. This whole concept of context-free grammar was invented. But the C programming language was invented only in the year 1972, meaning they had a lot of time for improving the CFG further and then coming up with a perfect programming language compiler, right? So they added few extra context-sensitive rules and syntax rules to make it more comprehensive and make the whole programming language usable for us for giving instructions to computers, right? So this whole thing. Now we'll see why still CFG, even after adding these kind of context-sensitive rules, it's not enough for NLP. For programming languages, adding these context-sensitive rules made sense, and we were able to come up with good compilers for the programming languages. But then, for our natural language, due to our complexity in our context, meaning, and the styles of poems, and all of these different 4 challenges that I told you, we were still not able to improve CFG to an extent that it is able to process the natural language directly. And that is why we had to go for some other better rules or some other better approaches. And that is how we came up with the first approach's second part, that is the heuristics and rules. So the next approach is the heuristics and rules. So first of all, what is this jargon? What are heuristics? We'll see first. Let me give you a real life scenario. Imagine you have a situation where you have to choose a particular option. You have 2 or 3 options with you in hand, but then you're not clear of the options. There's no clarity about each of the options. The problem is very much complex. So you're not able to identify which particular solution or which particular option should I pick up in your real life task, right? So in this particular scenario, what do? You usually connect or discuss about this with your peer or some person who has already gone through the similar kind of situation, right? Or could be even an elderly person, or could be even nowadays even people use LLMs for it. But then generally people brainstorm about these kind of difficult tasks or difficult options or ambiguous options that they have in hand by brainstorming about these options with a person who has already gone through or faced a similar situation in their past, right? So how are the people who have already faced a similar situation are able to come up with a solution faster or quicker? If you observe carefully, those people whom you would have approached for getting an advice about a solution, whom you have assumed that they would have faced a similar situation, they would have faced a similar situation before, they would come up with a solution, or they would have come up with a particular option in a much shorter span of time than what you could have done if you had spent the whole time getting clear on each and every option that you have in hand, right? Why is this the case? And take even a simple example, like say you're about to do some particular chore in your home, some particular chore in your home chore. So there is this household activity that you have to perform, but then you don't know how to do. So you specifically ask your parents, "Oh, what should I do for this particular task?" So they immediately, without even thinking or without even taking a longer time, they will give you an answer within some specific shorter duration of time. How is that the case? Because they have come up with a mental shortcut or an intuitive feeling or an intuitive uh, gut feeling for solving this problem, right? Because they have experienced a similar kind of situation in their past. This is exactly how heuristics strategies are and how heuristics actually works, right? It comes up with a short mental shortcut for solving a problem where the problem is complex or the data sets are not available for this particular problem. But then they approach the same problem with extrapolating their knowledge from their past where they would have faced a similar kind of situation, right? This is exactly heuristics. So heuristics are mental shortcuts or rules of thumb that simplify decision making and problem solving process. So they simplify the whole process by coming up with intuitive gut feeling with their knowledge that they've gathered from their past experience. This is exactly what is heuristics. So using the technique, you'll be able to make decisions faster, and you can even approach or face a complex problem with limited data set with this kind of approach. Fine. So this could actually include all of the strategies that we have. So heuristics can actually include all of the strategies that we have. You could even include the numerical methods, like we can even have a particular numerical weightage to heuristics. So there's even this term called as heuristic score. So they even numericalize the heuristics itself, and then they come up with a score for it, and they use it for any of the algorithms or particular decision task. For example, I'll give you another example of how this heuristic scores are actually used. Most of you would have used this application called Google Maps, right? So there, whenever you choose a particular location, your current location and your destination, and then search it out to find the path, it will give you the nearest path or the shortest path. How is it even doing this? It's using an algorithm called as A star algorithm. In that algorithm, they use something called as heuristic score for identifying the shortest path or the optimal path for you reaching your destination. So this is exactly how humans actually think. Humans apply their intuitive gut feeling to solve a complex problem, right? We're applying the same kind of framework of thinking even to our NLP tasks, and that is how we came up with these heuristics and rules. So we have the strategies of heuristics or of how to approach a particular NLP task. So they have to make it into rules and regulations, right? So that is why all of these rules and all comes into place. So that's why it's called as heuristic rules, right? Strategic mental shortcut based routes is the full form of heuristic routes, I would say. Fine. So you can see this image also. So they make the heuristics act as the ignition needed for solving a particular complex problem in the shorter duration, right? So this is it. Now we'll see the heuristics and rules approach for NLP tasks. So the main components of this heuristics and rules is that the developers who are developing the NLP solutions using this heuristics and rules framework, they'll have to have a deeper understanding of language. So there should be an expert in the linguistic domain, right? This is one criteria that is specifically needed. And if you have seen or observed for the context-free grammar, the person who invented context-free grammar, Dr. Noam Chomsky, he was a renowned linguist. So that profound is the linguistic studies for developing NLP tasks in the past. So it was needed in the past because they did not have different approaches like deep learning or machine learning in the past. So they will have to have the linguistic domain knowledge to come up with the rules and regulations to directly use them for their NLP solutions, right? So that was one component. The other one, what we have done, what we can observe in the heuristics and rules approach is that people started digitizing the dictionaries and thesaurus. So all of the dictionaries, they were digitized. They were actually first compiled properly from the start to the end, and then they were made into a digital format. And these digital dictionaries, they evolved with every iteration, and then that is how the knowledge bases came into picture. The difference between the digitized dictionaries and the knowledge base would be mainly this. The knowledge bases have even the comprehensive semantic relationship between the words. So dictionaries have only the words and their meanings, right? Just synonyms, that's all. And the usage, say, like for a particular word, how this word is being used in a sentence, that could be the highest amount of knowledge that you can gain from a dictionary. But then if you see a knowledge base, what they have done is they came up with a concept called knowledge base where you can even capture the relationship between the words. All right. So a word and another word, both how are these two words are actually linked? They link it using an edge with a particular relationship, right? So those relationships could be some meaningful relationships, and some examples of such relationships could be the meronyms and the hyponyms. I will be discussing in brief on what these meronyms and hyponyms are in the next section. For now, just understand this. So, how are these heuristics and rules applied in real life NLP tasks? So, here is an example of lexicon based sentiment analysis. So, what is a lexicon? First of all, let me brief again about what are lexicons. Lexicons are the smallest unit of meaningful components in a text document or any linguistic materials, right? So, any meaningful unit that gives meaning independently could be called as a lexicon, right, for a specific document. So, say for example, you have a collection of documents that have the reviews submitted by clients for a particular company. Okay. So, different clients are there for a company, clients meaning the customers, and they're giving some reviews about a particular company. This company has provided the services and solutions at the correct time. I really like their performance. I really like or I love their work. So these could all be their reviews, right? So all of these sentences have something in common in them. All of these reviews would have the positive words. Those positive words would be like, love, excellent, good, great. All of these small, meaningful units, right? These lexicons, all of these have this common genre to them. That is, they're all positive words, right? So what we could do is this is a strategy what we're using. It's a heuristic strategy that we're using. What we'll do, we'll come up with a variable called as good word counter, and then we'll add the number of times this particular words are present in a document. Number of times the good words like good, great, excellent, all of these positive words are there in the document, and then we'll get the number of good words in the document. Similarly, we'll do that for even the bad or negative words. So positive words are collected, number of positive words and the number of negative words could be collected, and then they could be compared. And if the number of positive words is greater than the negative word, then you could classify the document as a positive document. Right? That could be a sentiment analysis, simple sentiment analysis task using just the rules alone without getting into making a system that understands the whole language properly. Instead of doing that, we're using a shortcut here. That is the heuristics, right? So we are directly adding the number of positive words and then getting the number of positive words and then the number of negative words and then comparing those. And then with that comparison, we're getting to know whether this particular document is positive or negative. So that could be your simplest heuristics and rules-based, lexicon-based sentiment analysis, right? So this is an example. Now we'll see how this WordNet and other relationships look like, right? So this is the example of rule and heuristic rule-based knowledge base. So what you're seeing to your left is your WordNet. So I told you it's a digitized dictionary plus some external or some additional semantic relationships. So what are these semantic relationships or meaningful relationships? Here it could be this. I'll show you. So for the word sport, this is just a network or word network. What is this word net? Word net actually is the short form for word network, right? So we are seeing the network for just one word, that is sport. For this sport word, we have several relationships. One could be like as a relationship that we are seeing here. This edge will represent the like a relationship. And then this node or this particular content that you're seeing here that could represent another word. Here it is the professional football, right? Sport is like a professional golf, and sport is like a professional tennis, and sport is like a professional baseball. So all of these different words like baseball, professional tennis, and all of these and all are related to this particular word called sport, right? So the whole word network is able to capture all of these different relationships between the words. That is the main highlight here. It's able to even get different relationships, like for example, what you can see here for sumo. Sumo is like a sport. Is a sport. Is a sport. And then your sumo is the grappling, wrestling, and wrestling. Is like this. So these are different semantic relationships, right? Yes. So this is how the word net says or gathers all of the different information and then presents it itself as a network of words. And it gives out good semantic relationship between the words. Right? This is how they're way better than dictionaries. Fine. So now we'll see the different relationships. I'm just giving you just two examples of types of relationships. But then there are different types of different varied sets of relationships. If you go in depth into linguistic studies, you'll understand there are several different types of relationships between the words itself. So here we have hyponyms. Hyponyms capture this type of relationship. So apple is type of fruit. So apple could be one word, something like this here, and then you could have fruit, something like this here, another word. So the relation between these two words could be a hyponym. So this type of relationship, that is what it's capturing. Similarly, for meronyms, we have it captures is part of relationship. So TV is part of mass media. This is an example of how this relationship between two words could be captured by, right? So meronyms and hyponyms. This is all the example I can give you for now. Fine. Okay, fine. So we are done with this word network. We have captured all of the semantic relationships. That is all done. Now the researchers are actually thinking. So is this how far we can go? Can't we go even deeper levels than this? Is this all the information we can have from analyzing or capturing some relationships? Can't we go deeper than the words? Is what the question they were actually trying to address. And they got the answer as well. So they went even beyond the word level information, and that is how they got the regular expressions, or called the regex. Regex is mainly used for text analysis, meaning even where we are here trying to analyze even the number of frequencies or number of times even the characters being repeated, or a pattern in even in the characters. So words also have some pattern, and the characters inside the word also have some pattern. They're trying to even analyze those patterns using regex, right? So there are some. They came up with several notations for regex. Those could be your I'll draw it here. Those could be your star symbol. That is a notation. And then you can have some plus symbol. That is a notation. And then you have this question mark symbol. And then there are a lot of several symbols. Hashtag was also a symbol. Yes, I think so. So there are a lot more notations in regex. Each of these notations represents something. So here what you're seeing here as an example, so they've come up with a rule. So what did we see till now? We saw some rules and regulations for words. So we had some semantic relationship between words. Before that, the context-free grammar, we had some rules for words, right? So here we have come up with rules for letters itself. So for character itself. So what is the rule here? So any string of the form of this form, it will be able to accept. So what is this form? So what does it represent is this particular flow chart. So any string starting with A and then continuing with B and then C and then again continuing with B, C, or ending after B and C ending with a D, that could be accepted by this particular rule based system. If there is an NLP system that accepts this particular rule, then it will accept all those characters that have this form A, B, C, B, C, and D. It will accept this string. It could accept even this string A, B, C, D. It'll accept this string also because this B and C are actually inside the bracket, right? And with the star. So B and C could occur at least once, or it could occur at least twice. But then always in this arrangement, first B, second is C. And then if it is repeating another time B, but then it should always have some C. Only then it can go to some other character. So it could be A, B, C, B, again C, and then D. Then it will be accepted. By chance, for example, if it is only A, B, C, and C, then D, even if you have D here, this string will not be accepted because BC is here, but then again it's not following another B. If it is competing with C, again it should come here, get to BC again, and only then go to D. Otherwise, it should come here, BC. After finishing BC, it should not even go to B. It should directly go to D. Only then this particular rule will accept this string, right? This is just an example for how regex can be used for accepting a specific strings, specific pattern having strings, right? Or a specific pattern having characters as group of characters making up the string, right? So this is just an example of how regex works. So it's interesting to know that this particular tokens rig function is actually a framework that is developed inside the Stanford Core NLP library. So you can actually use this token regex framework, use regular expressions there, and then identify patterns in the text itself. And what you're seeing here, regex, is majorly deterministic. Deterministic meaning that if it doesn't follow this properly, or if it is not, for example, if you're giving such a rule, for example, say if you're giving such a rule and then equate it and making this as a condition, the system or the NLP system with this kind of a rule will not even accept any sentences or any strings without this pattern. It will be very much deterministic. For example, okay, instead of this rule, if I give another rule, for example, if I say it should have a word or a group of text called as good. Good is the group of characters that I'm giving as a rule here. So any group of strings that have this word good in it, or it has good only in it, only then will be accepted. So it has to exactly match this GOOD properly. Fine. If it is even DOOG and if it is only one of this, then it will not be accepted. Right. So that kind of a system we are actually seeing. So it is very much deterministic. It has to exactly match. Only then this would be taken into consideration, and then only then this would be taken as an input by the NLP system. That is why they had to come up with another approach that uses probabilistic regexes. So what it does is, instead of going for exact match, it'll go for probabilistic match. Here is an example for it. So for example, for the similar kind of operation, for actually this is a different wait a minute. Yes, this is okay. This is not the similar example. This is a different example, but then the notion is the same. So it's taking A and then it's continuing the path. If the probability of having B is more, or if the string has more B in it, and then if after B should have C, only then it can go for the end. If it is A, B, C, then it will end. Then this will be taking in the string A, B, C. If the string was A, B, C, then it will take in the string. If it was X directly, then it should be only X. Then there should not be any other string afterwards. But then if it is BC, again, if it's continuing another BC, A, BC, 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 then it could be accepted by this particular NLP system-based flowchart rule. It's an NLP-based heuristic rule using regex, right? So the probability, instead of going for exact match, we'll go for probability. For example, if I would say the same example that I told you, GOOD, good. So instead of going for exact match, even the string has GOO, the program will understand this particular probability regex will say, okay, out of GOOD, GOO is there, meaning there is more probability that this word could be GOOD. So we'll take in this particular input. That is what it'll do. So that is the probabilistic regex. So these are the two different approaches we developed so that we could do intrinsic text-based analysis by giving a pattern for by underpinning the pattern for even the characters inside a text, right? So till now we have seen all of the fundamental concepts that are used in this second approach. Second part, that is the heuristics and rules. Fine. Now we'll get into the tools that are used in this second approach. It is all rules, right? So here's an example outlook of this particular tool called as GATE tool. GATE tool is a general architecture for text engineering. A separate tool they had for doing text engineering in the past, right? In the 90s and all. Fine. So they used something called as the Java annotation pattern engine. This was the back end of this tool. And this was mainly developed to model complex rules that included both the CFG and the regex. So they were able to take up the CFG based rules also, and along with that, they were able to take in the character level analysis based regex. So using these two different approaches, this tool became very much popular. It was all very widely used. Fine. This is an example of how this tool used to look like and how it worked. So that's some ontology, how different words are actually connected to each other. This is called an ontology. Ontology is just a term that we use for getting the relationship between words, semantic relationships, and all of that. All of these different properties of the words. All of this was actually captured, and then they were doing some analysis based on these different texts, right? But these were all heuristic based. So they had their own limitations, but then they were useful and verifiable. Most importantly, all of these techniques were verifiable. That is a major advantage that they had, right? And that is why if anyone asks you, or if you ask this for yourself, if you have this question now, is heuristics even now relevant? Why am I even learning this? If we have this doubt, let me clarify it now. This snippet that I've actually posted here is actually from the book called the Practical Natural Language Processing book, right? So that book was actually released in 2020. Even in 2020, all the medical institutions were still relying on heuristics. And even now, even in 2025, many of the hospitals, clinics, all of them rely on this kind of NLP, heuristics and rules-based NLP system to retrieve their electronic health records, of their patients. So all of the patient details that are stored in the computer, they retrieve the data for a particular patient using heuristics and rules approach. That is their fundamental NLP solution that they have. Why so? Because though we have better models now, like the large language models and the machine learning techniques, all of those are there. Even then, they're preferring this because all of these deep learning or any of these approaches are a black box. We are not able to see how these conclusions or retrieval of data has happened, or how we are not able to properly, explain why a particular response is given by a particular model. Meaning, we are able to see what are these weights, like what are these parameters inside the model. But then we're not able to say how exactly, which conditions has it used to come up with this particular response or this particular data retrieval. So that is the main issue with the deep learning or machine learning models. This is their whole black box perception limitation. And that is why, since we cannot risk such a mistake, if by chance, if a particular retrieval of data which is not explainable has some mistake in it, if it has some bad impact, the worst case scenario would be losing a life that is very much precious, right? Invaluable. That is why even now in the hospitals and medical institutions or even the pharmaceuticals, they use heuristics and rules for their NLP tasks based or drug based NLP tasks or even electronic health record based NLP task and all of that. Fine. So heuristics and rules are still even relevant, even in 2025. Though they are still relevant for the all of these healthcare or pharmaceuticals or the hospitals, for other domains other than these, we wanted a better NLP system. That was very much clear. We wanted a better NLP system that could capture even the complexity, natural language's complexity, and the ambiguity that we have in our day-to-day language that we are using. Right? That is why we had to move forward. We have to improve our past technique. So that is why we came up with the second approach. Second approach is the machine learning approach. Right? So till now, what and all did we see? We saw the first approach's first part, that was the context-free grammar. We saw its applications and all of that in detail. And then we saw the first approach's second part, that is the heuristics and rules. We are wrapping up this first lecture's first video, and it will be called the first part. So till now, we have started with the introduction to languages, and then we proceeded further and then completed till the first approach to process languages, right? So this is what we have seen. Before going into the ending portion, let me just give you a data point here. So what you're seeing here is the viewership for with the number of lectures, right? So you can see for the first 5 lectures, there were a lot of views, and then afterwards it went down. So why is this the case? Even though this is actually a data point for a popular lecture series, which was praised by many of the leaders in AI research and tech professionals in product companies like Google, Amazon, and all of that. Even then, even though the quality of the content was very good till the 30th video, still many of the viewers did not even complete, because most of them, when we saw, were actually students and they haven't really completed the whole course or lecture series. That's because of their inconsistency and lack of discipline. That is why they were not able to complete the whole course. So if you really are serious, I want you to be in this 5% who completes the whole course and gets the overall knowledge and skill sets, right? So make sure that you complete the whole series, and make sure you have the discipline to be consistently putting your effort for this whole cause of getting this NLP skill sets, right? Make sure that you're putting the efforts consistently to view all of the content starting from the first minute till the last minute, so that you get an idea and you get the whole comprehensive knowledge and the skill sets needed for cracking even the NVIDIA associate examination. Fine. Fine. So we'll see what we'll see in the second part. In the second part, we'll cover the second approach and the third approach, of course. And then along with it, we'll cover the NCA exam syllabus briefing. So NVIDIA Certified Associate Examinations briefing, we'll be looking into it. Fine. So that was all for the first part of this video. See you in the second part. Fine. Have a nice day.